plus 4x squared, right? If you let that be u, what's the derivative of that? 8x, and you have an x out here, don't you? So you're off by a constant. So it'll work. So equal ... So that one didn't require a whole lot of algebra to get to our final cleaned result. I'm putting ... just because we could do it, right? Okay. Let's look at one last one. X is equal to 4 minus y squared. Sorry, square root. X is equal to square root of 4 minus y squared. And y is between 0 and 2. And I want to rotate this around the y-axis. Same formula, right? This is the same because I'm going around the y-axis. But my ds, I'm going to want to have my ds use the dy at the end, right? Because I have that solved for x. So I want this to have a dy at the end, which means when I go to my formula, it's 2 pi integral. This is still x, right? Yeah. But this in here is going to be my x prime, right, squared. Am I going to need to replace x? Yes. What am I integrating with respect to? Y, right? Integrating with respect to y, which means that I can't have x here. I have to replace x with something with y's in it, don't I? Well, that means I'm going to have to replace x with this. See the difference? Yeah. Okay? In this problem, if I'm going to use this formula and integrate with respect to y, this is good. It's good right here, right? Because I have x solved for over there, so x prime is going to be easy to do. This part is not as clean, though. That's going to have to be replaced. So let's do that. This is, let's find our derivative. X prime is 1 over 2 square roots of 4 minus y squared. So that's derivative square root of something. Then times derivative what's inside. So negative 2y, right? That go away. We should just have negative y over square root of 4 minus y squared. I need to square that. When I square that, I get on top y squared because the negative is going to become positive. And oh, again, very nice, 4 minus y squared. The root goes away. And I have to add 1 to that now, right? And we've played this game before, right? We get a common denominator. So when I get a common denominator between those two, I'm going to introduce a 4 minus y squared right there on top and bottom. And then I'll have plus y squared. Oh, man. And they're going to cancel out. And I'm going to have over 4 minus y squared, which is 4 over 4 minus y squared. That's going to be underneath the root, right? Wouldn't what? You can't split these, right? Because 2 here, 1 here. You can do it the other way, but not with that. All right, so I'm going to have to take the square root of this, right? Up there? I'm going to do that right now. I'm going to do square root here, square root here, square root here, square root here, and that would be equal to 2 over the root of 4 minus y squared. So 2 over the root of 4 minus y squared. Do you see just how absolutely nice this is going to be? Y'all see that yet? If I go back to this integral, 2 pi, what's my integral going to go from? 0 to 2, and then x, right? But x, I can't have x's here because I'm integrating with respect to y, so x is going to be replaced with square root of 4 minus y squared, right? But then times this thing, which we already said is this. I mean, could it get any better than that? Really, could it? No. Look at that. I get a constant, don't I? And I can pull the constant out if I wanted to. I can pull the 2 out, I get 4 pi integral 0 to 1, or 0 to 2, sorry. 0 to 2, right, of 1 dy. And what's the antiderivative of 1? Y, right? And then we plug in 2 and plug in 0. So at the end of the day, this can turn out to be 8 pi. You can do it yourself, but that's what it would be. What do you think? What do you think? What do you think? What do you think? Okay? So I just thought of something. Was that me? Yep, that was me. Oh, wait a minute. Yeah, okay, yeah, we can do this. We can do this. This will be fun. We're gonna do all of these. This is gonna be pretty cool. So we have taken a circle of radius r, haven't we? We've shown that the area is pi r squared. We've shown that if you create a ball, solid ball, that the volume was 4/3 pi r cubed, right? We have shown that the circumference of a circle radius r is 2 pi r, right? We have not talked about the surface area, have we? What's the surface area of a sphere of radius r? Let's see. So how do you think I'm going to do it? I'm going to take a quarter of it, and I'm going to wrap it around my choice. X or y axis, doesn't matter, right? So if I take this quarter and wrap that around the x-axis, get the surface area, then that'll give me half of the surface area of the whole thing, right? Or if I go around the y-axis. Let's see which of those looks preferable to you. If I solve this for y, check this out. This is going to be pretty awesome. I keep on saying that, but I really do believe it. Okay, then that's what our equation would be, right, for that? If we wanted to go around the x-axis, then we would have to use the formula that says 2 pi, so this would be x-axis. We would have to go 2 pi integral, and then it would be what? Y, and then ds, right? If I go around the y-axis, I'm going to go 2 pi, and then I'm going to go x ds, right? So maybe we can decide which of these looks better to us. Why? Because I think we want to know why. This one? Why? Because what would you do with the y here? You'd replace it with the square root thing, right? Ooh, that might get ugly. What about the ds? Which, what are we going to do that with respect to x or with respect to y? X. With respect to x, right? Yeah, so let's do that. Let's do that one. This will be 2 pi. We're going to go everything with respect to x. So if I go with respect to x, what are my limits of integration? 0 to r. We've done this several times, right? 0 to r. And then I'm going to have to do y. I need more room. Okay, this is going to be 2 pi integral 0 to r. I'm going to do y, which is the square root of r squared minus x squared. I'm pretty scared of this right now because that's not very pretty, especially because I have more to put in here, right? Square root of 1 plus. Now I need some derivatives, right? So let's get the derivative of that. I'm trying to find y prime here. Y prime, right? Okay, y prime is 1 over 2 roots r squared minus x squared times negative 2x, right? Negative x over this root. Square top and bottom. X squared over r squared minus x squared. Does this look familiar? We just did a problem almost exactly like this, except they used 4 instead of r squared. So plus 1, add 1 to this. So I'm going to try and see. If I added 1 to that, the 1 would become r squared minus x squared over, and it would kill off an x squared. So I would get r squared over r squared minus x squared. I'm just trusting you could add 1 and get the common denominator and do that. And then I need to take square root of that, right? I'm going to do it right here.
So it would be
R over square root of r squared minus x squared. And then they're going to cancel. Isn't that nice? Am I moving too fast? You'll get the build up on that? And so this is going to be r square root of r squared minus x squared dx. Cancel, cancel. R is a constant. I can take the r out. 2 pi r integral 0 to r of 1 dx, which is just x. So this becomes 2 pi r times x evaluated 0 to r. So you plug in r and you get 2 pi r squared. And you plug in 0 and you get 0. So this is the surface area of a sphere, radius r. That was pretty cool. So we have, I know it's right, but I'm just going to look at the formula sheet just to get that feeling, you know? Yeah, wait, oh, our answer is not 2 pi r squared. It's 4 pi r squared. That was half. Sorry. That's half the sphere. Okay, double it. So the volume of the sphere is 4 pi r squared. Okay. One last problem that has to do with this stuff. And I think after this problem, if I'm not mistaken, we get to move into chapter 8, or we can do some applications. And I haven't decided what I want to do yet. So let me do this problem first. This is a famous problem. Oh, you know what? I had already written it all out. I didn't print it, but I wrote it all out. Where is it? There is a famous problem you may have heard of. Anyone ever heard of that before? Gabriel's horn? Gabriel's trumpet? Sometimes it's called Gabriel's trumpet. Okay, so here's the problem. We take the function 1 over x, which looks like this. It actually goes like this also, right? But we're only going to look at it between 1 and infinity. So this thing goes forever in that direction. We've talked about improper integrals already. And so if we asked for the area under this, the area underneath this, we could do it, and it would actually diverge. It would become infinite. We showed that in class. But Gabriel's horn is a different problem. What it is you take this function that goes out to infinity and you wrap it around the x-axis. And when you wrap it around the x-axis, you get this shape called Gabriel's horn, or Gabriel's trumpet. It's like a trumpet, right? But it's like an infinite trumpet. All right, so the end of this does not exist. It goes forever. It gets thinner and thinner as you go. So with everything we've talked about, we could try and find the volume of this if we wanted to, couldn't we? Now, it would be an improper integral, but it would be something we could do. We would need to say, okay, we're going to integrate from where to where? 1 to infinity, and we're going to have to use pi. Right? Integral from 1 to infinity, and then the function squared. That's the formula for revolving around the x-axis, right? Top function was 1 over x, bottom function is 0. And if we do this, we square that, which really becomes that, right? Bring the negative, or bring it up. And then take the antiderivative, just use power rule. I get this. And then I'm supposed to use a limit. Technically, I'm supposed to use a limit because this is an infinity. But I could just say 1 to infinity and just think of it as a limit. Like what would happen if I let that x become infinite? I get negative 1 over a huge number, that would go to 0, wouldn't it? So this would go away. But if I plug in 1, I would get just this. And so at the end of the day, you get pi. Okay? So this horn, this Gabriel's horn or Gabriel's trumpet, this thing has a finite volume. Has a finite volume. Even though it goes forever, the volume of this is finite. Okay, what about surface area? Well, surface area, I would have to do the integral 2 pi, right? Integral from 1 to infinity. Then I would have to have y. Y is 1 over x. And then square root of 1 plus the derivative of x squared. Now I already did the derivative here. So here's the derivative, and then I squared it, and then I put it in here. And when I look at that, this integral right here is actually very difficult to do. All right? So I want you to just look at something. Do you see this expression right here? Do you agree with me that that expression right here is always bigger than 1? No matter what you plug in for x. Because if I'm going to take a number and I'm going to raise it to the 4th power, that's a positive number. So this is some positive number out here. And 1 plus a positive number is a positive number. And the square root of a positive number is a positive number. But they're all bigger than 1. Agreed or not? Yes? So if this number is bigger than 1, right? If this is bigger than 1, then whatever this integral is would be bigger than or equal to the integral without that root there. Just imagine that root, I've replaced it with 1. This 1 is smaller than this thing, right? So the area under that must be bigger than the area, the surface area of this must be bigger than the surface area of this. Do you buy that? Sure? I mean, it's correct. I just want to make sure you buy the logic behind that. This integral I could do, because the antiderivative 1 over x is natural log of x. So what we get, if you do that integral, is that this becomes 2 pi natural log of x. You take a limit, and then you plug in a 1. When we plug in 1, this just goes away, because natural log of 1 is 0. But when you plug infinity in the natural log, it becomes infinite. And so this diverges. So this integral becomes infinite, and this one is bigger than that, which means this must also be infinite. Buy it? So this problem is actually known as the paradox of Gabriel's horn, not Gabriel's horn. It's known as the paradox of Gabriel's horn. Why is it a paradox? Why is it weird? So I've got this funnel, right? Just imagine like an infinite funnel. We're saying that we could fill this funnel up with exactly pi amount of paint. But we would never have enough paint to paint it. Right? The surface area is infinite, but the volume is finite. I just wanted to show that to you. That's all. We're not going to get into what, because there's a lot of arguments as to why it's like this, and it gets to beyond the class. I just think it's a cool example of how we could take something and find its volume and surface area and come up with something weird at the end. All right. So I'm going to give you all a choice right now. We can move into chapter 8, and we can take the application problems and save them till the end. And with the applications, let me try and explain something the way this works in math. There's many applications with integrals, all right? In physics, chemistry, biology, you can do a lot with integration. I can't sit here and teach everything about physics, how we could use integrals to do work, right, or something like that. The book has one section, which is about 1, 2, 3, 4. It's about maybe 10 pages, and they say, okay, well, here's some things you can do. We can do work, all right, in physics. We can do hydrostatic pressure and force. It's like another application. We can do moments and centers of mass of objects. And that's it. Okay, so they give you they give you a couple of things that you can do with integrals. We can either tackle one of those things. So I'm only going to do one. I can't do all three. I can do one of those right now, or we can start to move into chapter 8 and revisit that later. So let's take a vote. I'll give you a couple of seconds to think about it. You want And I'm thinking that I know people want to do work, but I want to do center of mass. That's what I would prefer to do. How many of you want to see the center of mass? I mean, you're not going to upset me if you don't want to. One, two. Center. Okay, so we're center of mass. All right, we'll do center of mass then. We'll do center of mass. So this is one application of integration. And I'm going to have to destroy my beautiful artwork from the other day to do this because I wasn't quite prepared for this. Oh, yes, I know. Hours of work, hours of labor. Yeah, you want one last look? There you go. Say goodbye. So what I'm doing right now is I'm creating a very strange looking shape out of cardboard. There we go. I'm trying to make this as awkward looking as possible. There we go. Yeah, good enough. There we go. Okay, so we're going to talk about center of mass. Now I need to kind of clarify a few things. First of all, we are talking about two-dimensional objects, okay? Not three-dimensional. If you want to do three-dimensional, in Cal 3 we find centers of mass of three-dimensional objects. But everything that we do here extends over into 3 dimensions, all right? So when we talk about the center of mass of a flat surface like this, we call this a lamina, okay? That's what we call it, a lamina. And we are trying to find the center of mass, which would really mean the point on the surface where I could balance this. I could balance this on my finger. That would be the center of mass. Now in physics, that's useful because a lot of times we have complicated looking objects that are in motion, and instead of looking at them as a complicated object in motion, we find its center of mass and we look at it as a point mass moving through space as opposed to some weird shape moving through space. So it's important to find centers of mass of weird shapes. So physically, here's how we could do it physically, then I'll show you how we do it with the math. Physically, what we could do to find the center of mass is you could actually take like a needle and stick it through this cardboard and hang this, and then hang like a plumb string down with a weight, and that would be going to the center of mass of the Earth, right, the gravity, and it would form a line. So if I drew a line straight down, right there, I would get one line, right? Then I go and I pick some other point, and I do the same thing, and I hang it straight down, and then just for kicks, I do maybe one more, and I draw that straight down, and wherever those lines intersect is your center of mass. Now, I mean, I obviously did not use a ruler or anything else, but I'll see how close I was. I'm a little off, but you get the idea, right? So that's how you could do it physically with a nice flat sheet. Now there's some things we have to kind of know about this sheet. What we're studying right now, what I'm going to show you, we're assuming that this lamina is what we call homogeneous. Now homogeneous means that, I'll do a piece of paper instead because I think you could buy this if I told you. Homogeneous means that the density at every point is the same. In other words, if I tore this in half, exactly in half, and weighed the two, they'd weigh the same, okay? And if I tore out an inch from here and an inch from here, they would weigh the same. They're homogeneous. Does that make sense? Now we know in reality that this is not truly homogeneous, right, this paper? Because there's wood fibers in here and there's whatever they use to adhere the paper. So if we had something accurate enough to measure, there would be discrepancies in the weight. It's not truly homogeneous, but for the sake of most things, it's close enough to homogeneous. Am I making sense? Some objects are non-homogeneous, and in Cal 3, we find centers of mass of things that are not homogeneous, which is more useful. But here, what I'm about to show you, we're assuming that we have a homogeneous lamina, and we want to find its center of mass. So let me start with the picture. And this is going to look real familiar to you. F and G. Okay? We've got F and G again, and we've got a region between them, don't we? Let's call that region R. That region R is a lamina. Can you imagine that that's this really, right? That's the shape of this. We would like to find the center of mass. Okay, so we are looking for the center of mass. Now that actually has a word, a technical word. It's called the centroid. We're looking for the centroid for this object. Now, the way that this works in two-dimensional space is as follows, all right? Let me label it. The center of mass is somewhere in here. Do y'all agree? Somewhere in here? Yeah. Okay, I'm just going to say that's it right there. That's the center we're looking for. We're trying to find that point, okay? That point, we're going to give it a very special x and y coordinate. It's going to be x bar and y bar. That's our center of mass. Here, what was that? You all right? That's what I just decided to call it, x bar and y bar. We're trying to find that. So here we go. Here's the formula. If you want to know what x bar is, oh, I need to put my limits of integration here, going to come from A and B again. The center of mass is going to be 1 over the area of R. So when I put capital A sub R, I'm talking about the area of that, okay? And then it's going to be integral from A to B of x times f of x dx. So I'm truly treating this right now as if like a physics class or like a class that's not a math class. I'm not here to show you where the formula came from, okay? That's a different lecture. That's a different thing, all right? This is an application of integration. If I want to know what this x coordinate is, what I'm going to do is calculate this. If I want to know what the y coordinate is, I'm going to do 1 over the area of R times the integral. Now this is going to be a little bit, this is going to look a little bit different. A to B, 1/2 times the function of x squared dx. Now the book, this is coming off of page 407. The book goes into some detail about how they got these, but I just realized that I forgot that I'm doing the region between two functions. Hold on, we need to edit this. We need to edit this. Sorry about that. I forgot I was doing two functions, not the area. I wasn't looking from F all the way down to the ground. I was looking from F down to G instead. So the formula is going to change. So this one's going to become f of x. Let's put the squared here, minus g of x squared like that, dx. There we go. That would be it. So those are your formulas. Did I leave the dx off? I did. Those are the formulas right there. Now, when you look at this formula, what are you going to need to do to get that? You're going to have to find the area. So that's a different integral, isn't it? So you actually have to do an integral to get the area first. Whatever that number is, you put it here. Here, you put that number, and then you do these formulas. So do you want to do an example of this? We can. Let's do it. Okay, let's find the centroid. Let's find the centroid of... Is it all right if I just pick one that I'm pretty sure we're not going to be able to do and that we use the computer to do it? Like to do all the integrals for us? That sound good? let's do this. Let's take the function f of x equals sine x and g of x equals x. And let's look at this just in the first quadrant. So sine x goes like this, right? And goes down, back up. And then f of x equals x does that. So this is y equals sine x. And this one is y equals x. Okay? You with me? I would like us to consider this region right here. Call that R. What is its center of mass? Assuming that it's a homogeneous lamina. Where's the exact center of mass of that object? All right? By the way, does the center of mass of an object have to be on the object itself? What do you think? No.
Do you know the tilted tower?
The which one?
Tilted tower.
The Leaning Tower of Pisa?
Yeah, the center of mass is outside of the
That's right.
outside of the thing.
Yeah, so that's why it's,
There's also
Yeah.
that bird that you point your finger to with the beak. Never mind.
a boomerang is an example of an object that has a center of mass that's outside of its own physical boundaries. Just think of a washer, okay, like a washer for a car, you know, like a bolt, right? Where's the center of mass of that? Right in the middle, right? And it's not on the object itself. So your center of mass does not have to be on the object. So we could possibly get a center of mass here that's not even in here. It could be out here somewhere. Okay, so let's figure this out. First thing we're going to need to do is what? Find the area, right? So let's try to find the area. So to find the area, I'm going to do an integral from where to where? 0 to, 0 to, 0 to there, right? Okay, so here we go. This is our first step to the computer. So I'm using Wolfram Alpha. I know some of you don't like that. But I'm going to solve, what am I trying to solve? Sine x equals x. Computing. Shoot. Is my graph no good? My graph's no good. Okay, we might have to change that. Let's change it to sine of x plus 1. There we go. Sorry, let's go change my graph. I should have used cosine, but change the graph to sine of x plus 1. And can y'all see it here? We're talking about this region now instead. Our region has changed shape a little bit. All right, I'll just leave that up there. Okay, and what is the solution? According to Wolfram, 1.934 something. So I'm just going to say, just for the sake of the fact that we're not trying to put a man on the moon here, let's just go 1.93. Is that okay? Okay, so our integral is going to go from 0 to 1.93 of what? Trying to find the area, right? So top minus bottom. So top function is sine x, so sine x plus 1 minus x dx. Do we agree? Yeah? Okay, I'm going to have the computer do that for me also. So I'm going to integrate sine x plus 1 minus x from 0 to 1.9, what did we say, 3? Okay. Does that look right to y'all? Did I type it in right? Okay, so let's say 1.42. The area here is 1.42. Got it? Okay, what's next? That's just getting the area. Now what do we need? X bar, which will be 1 over the area, 1 over 1.42, integral from 0 to 1.93, right? And then what? X times the top function minus the bottom function again, right? So sine x plus 1 minus x dx. Am I moving too fast or are y'all getting this? I'm using the computer because I don't want to take our time integrating. Okay, so here's x. Here's f of x minus g of x. That was the formula for x bar. And then here's 1 over that. So I'm going to type that into the computer. So I want to integrate that. The only difference is I want to put an x out front, right? And want to go from the same thing. Let me go ahead and get that answer first. I get 1.08. Where is it? 1.08. So this is going to be equal to 1 over 1.42 times 1.08, which is, someone do that real quick on their calculator. Take 1.08 divided by 1.42. 0.76. Okay? 0.76. All right, now let's get y bar. Y bar is 1 over 1.42 integral from 0 to 1.93, and then it's just your f function minus your g function, half of your f function squared. So 1/2 times your f function squared minus your g function squared. That's the formula I just put up on the board a second ago, right? So I'm going to have the computer do that for me. So I'm integrating now. Oops, I guess I can do that. 3.37, let's say. But then we still have to divide that. So this is 1 over 1.42. Then I still have 1/2 out there. Then this was 3.37. So I've got to do that. Who's got that for me? Anyone? 1.19. Okay. 1.19. And, yeah, is that all right? So if I go back and I look at that graph again, our centroid is 0.76 and then 1.19. So I'm going to have the computer graph it again for me. Graph. Graph sine x plus 1 and x on 0. And let's go 0 to 2. See if it's smart enough to interpret that. Yeah. Okay, there it is. Let me move it up there. All right, so for this region right here, assuming that it is a homogeneous lamina, the center of mass is 0.76. So here's 0.5, 0.6, 0.7, 0.6, somewhere around there, and then 1.19. 1.19, so somewhere around there. So somewhere around in there is the center of mass. Okay? You see how quickly with the computer you can do something like that? If you know what integrals to use, right? You don't even need your techniques of integration. You just go and get it done. Okay, so we are done. Oh, I have something for you. Almost forgot. I have a take-home quiz for you. Here we go. And we do need to talk about this, and I do have 2 minutes left, I think. I'll get the extras in a second. Just get these handed out. Almost got out of here without it. Almost made it. I figure y'all don't have anything to do this weekend.
So is this due next week?
Yeah, so I'm going to make this due on Thursday, all right? That doesn't mean you should wait till Wednesday night, okay? But
Next Thursday?
yeah, because today's Tuesday, so next Thursday. Yeah, sorry. No, next Tuesday. Sorry, next Tuesday. Next Tuesday. I keep on thinking it's Thursday. All right. Next Tuesday, a week from today, all right? This is due. It says, for all the problems below, set up the integrals. Do not evaluate them. Include a detailed sketch for each problem. Do your work on separate paper, but put your final answers below. Staple your work to this page. So I expect to be able to flip back and see how you got to your answers, right? This is pretty straightforward. I give you a region that's bounded by some curves. You need to be able to draw it. You need to be able to find its intersection. The intersection of these curves you need to find, and you need to find them algebraically by hand, not with Wolfram Alpha, all right? So that should be included in here. You can use Wolfram Alpha to help you to verify your answers, but you need to algebraically get them. Area, and then there's a bunch of rotations, okay?
So next week on Thursday.
Tuesday, a week from today.
Just making sure, because
Yep.
you said Thursday.
I know I did. A week from today.
Now everyone hates me because,
No, that's not why they hate you. That's not why they hate you. I'm going to count this as 2 quiz grades.